Welcome you all. So, in this lecture I will talk about the concept of continuous functions for multivariable functions. So, in my last lecture you might have kind of seen that I talked about the concept of limit for functions from Rn to Rm. Now, and various properties I have talked about, and then this lecture I will talk about the notion of continuity for functions from Rn to Rm. And of course, you will see that once I have the notions of continuity, then like I can write my kind of functions from Rn to Rm as m components, and then what sort of interplay that component functions with the original functions will be there. So, along with I have already talked about like the concept of compact sets, connected sets. So, at the end I will also discuss like what is the interplay between continuous functions and compact sets and connected sets. So that is this lecture's plan. So, let me just with the definitions of or notions of continuous functions from Rn to Rm. So, that means now let us start with a function f from Rn to Rm. So, okay. So, before that let me just recall the notion of continuous functions from say real valued functions with real variable. Okay. So, that portion we are familiar with that. So, if I have a functions from R to R, what do I mean by the continuity of f at some point? Okay. So, let f be a function from D subset of R to R, that means real valued functions with real variable. So, let us take a point x naught in the domain set D. So, the continuity of f, I will say that f is continuous at the point x naught if something is true. And what is that? So, given any epsilon positive, there should exist a number delta which is also positive. Look, delta may depend on the point as well as epsilon, such that whenever I have the distance between x and x naught is less than delta, then the distance between fx and fx naught should be less than epsilon. So, what does it mean? So, that means I am talking about the continuity of f at some point x naught. So, what I am doing is that, so take a point, if suppose I want to talk about the continuity of f at x naught, given epsilon, if there exists a delta, the delta depends on the point and epsilon such that if x belongs to the neighborhood of x naught with radius delta, the ball of center x naught radius delta, in fact ball means I should say that it is an interval with center is x naught and radius is delta. That means if x belongs to, so I think I should not write like that, it should be like x belongs to x naught minus delta, x naught plus delta. So, that means given epsilon, if there exists a delta such that if x lies between x naught delta to x naught plus delta, x naught minus delta to x naught plus delta, then my difference between value of f at x minus f of x naught should be less than epsilon. So, that is the definition of continuity for real valued functions with real variable at the point x naught. Now, this time unlike in the case of limit, I told you, if you remember, that to talk about the existence of limit of a function f, the point x naught need not be a point on the domain of f. However, in the context of continuity, I need that the value of the function at the point x naught. So, therefore, if I want to talk about the continuity of f at x naught, I should start with the point x naught inside the domain, and then I should talk about the continuity of f at x naught. So, this kind of definitions you are familiar with for the real valued functions with real variable. This is a picture I have written for examples. So, if I want, suppose this is kind of my function, this is the graph I have written. So, suppose I want to talk about the continuity of f at the point 2. So, what will happen? So, if I take a very small, so that means what? So, that means I want to talk about the continuity of f at 2. So, go to f2. So, this is my point f2. Okay. So, what will happen given epsilon, that means if I have this small neighborhood surround the point f2, that means this is the one f2 minus epsilon, f2 plus epsilon, then I need to find a neighborhood around the point 2. That means I need to find a delta such that if x belongs to this set 2 minus delta to 2 plus delta, then the value of the functions, that means this is the value of the function, should lies between f2 minus epsilon and f2 plus epsilon. So, that is kind of definitions, like it is called epsilon delta definitions. Now, there are various like equivalent kind of way I can talk about the continuity of f, like I know there is a sequential criteria for the existence of limit. Similarly, there is a sequential criteria for the existence of continuity that I will talk about later in my slides. So, at least this is the notion of limit of continuity for real valued functions of real variable that you people are familiar with. Now, let us see what sort of definitions of continuity I will have in the context of several variable functions. Okay. So, before that, let us just look at some examples of continuous functions for real valued functions of real variable. So, look, I have written, so examples of everywhere continuous function on R. So, what is? So, polynomial is a very nice function which is continuous everywhere. Sine function, cosine function, these are also continuous function. Exponential function, these are also nice function, these are also continuous functions everywhere on the real line. So, since I have given the examples of continuous functions, so one can ask, okay, give some examples of nowhere continuous functions or continuous function which is not continuous everywhere, something like that. So, this is, I have given one example which is nowhere continuous functions, and I think people might have familiar with that kind of functions. So, f(x) taking the value 1 if x is rational number, and f(x) taking the value 0 if x is rational number. So, f is a function from R to R. If x is a rational number, it is taking the value 1. If x is an irrational number, it is taking the value 0, and one can easily check that f is not continuous at the point x naught. In other words, as I just said, that to talk about the continuity of f at x naught, you just use the sequential criteria. Since f is taking two different values, if x belongs to rational, it is taking one value, x is irrational, it is taking one value, you just take the sequence. Suppose I want to talk about the continuity of f at x naught. So, once I have a point x naught, suppose this is my point x naught. So, what you do, first you take two different sequences, since rational number and irrational number are both dense in R. So, given a point x naught, I can choose a sequence of rational number which converges to x naught. Also at the same time, I can choose a sequence of irrational number, this also converges to x naught. So, but if I go to rational sequence, it will give the 1 value. If I go to irrational sequence, it will give the 0 value. So, that means I have two different sequences, both converges to x naught, but the corresponding image sequences, that means f(x)n and f(y)n, they converges to two different limits. So, therefore, my function is not continuous at x naught. So, this is a very bad function. This is an example of nowhere continuous functions. Okay. So, another function, it is actually continuous, but it has a discontinuity at finitely many points. So, for example, this is the function f(x) is equal to box s, or sometimes this is called the integral part of x. So, this is the picture I have drawn here. So, this is my x axis, this is my y axis. Okay. So, suppose this is the function, so this is the picture. So, it is taking value from 0 to 1. So, that means it is taking from close 0 to open 1, it is taking value the 0. But whenever it crosses 1, so closed 1 to open 2, it is taking the value 1. So, that means I can write it like that. So, f of x is equal to 0 if if 0 is lesser or equal to x less than 1. It is taking 1 value if 1 lesser or equal to x less than 2, if it is 2, if 2 lesser or equal to x less than 3, so on. Similarly, if I go to the negative 1, so what will happen here? It will take the value -1 if x, or if -1 lesser or equal to x strictly less than 0. So, this is called the integral part of x or box x function. So, that means if I draw pictorially in x axis and y axis or in R2 plane, so that means in 0 to 1 it is taking like 0 value, once it crosses 1, 1 to 2 it is taking 1, and of course, in the left hand side from 0 to -1 it is taking the value what, -1. Okay. So on so forth. So, this is sometimes called, this is also step functions. So, what can I say about the continuity or discontinuity of this sort of functions? So, these functions is actually continuous at each point here. However, it is discontinuous at 1, at 2, at 3, because at 1, at 2, at 3 it has a jump. Similarly, at 0, at -1, at -2 it will have a jump. So, therefore, I can say that this is a discontinuous function at all integers. However, it is continuous if I take out the set of all integers from real line, it is actually a continuous function. Okay. So, this is another way I can think about the concept of continuous function, again for real valued functions of real variable. So, look, whatever epsilon delta definitions I have given, similar sort of thing you can see it pictorially. So, that means what I am trying to say is that if I have a function from say some subset S of R to R, and if I want to talk about the continuity of f at the point A, so what will happen, that this is like in language you can say continuity of f at the point A. That means nearby points of A should be mapped by f to a nearby points of f(a). What does it mean? So, that means if I start with a point A and I want to talk about the continuity of f at A, that means if I take a neighborhood of f of A with some neighborhood, that means given epsilon, take a neighborhood of the point f of a, that means f a minus epsilon and f a plus epsilon, then there should exist a delta, so that if I consider the neighborhood a minus delta to a plus delta around the point A, and if I take the image of that neighborhood a minus delta to a plus delta, and if I apply f, that should fully contain in the interval f a minus epsilon to f a plus epsilon. That exactly I have written. So, okay, so suppose for example here, so I have a point A here. Okay, so I have a point f a here. So given epsilon, consider the neighborhood of f a. Okay, f a minus epsilon, f a plus epsilon. Therefore, their corresponding say neighborhood of a minus delta, a plus delta, such that the value of f of this full interval should fully contain in here. That's exactly I have written. Similarly, if you go to here, so I have a, I have a f a. So I want to talk about the continuity of f at the point A. What I will do? Start with a neighborhood of f a. So this is kind of some ball. So start with a neighborhood, that means given epsilon, start with a neighborhood of f a. So what I want neighborhood of the point A in the domain side. That means it should depend, given epsilon, I should find a neighborhood in the domain side A such that f maps the full neighborhood into the open neighborhood of f of a. So that means I am pictorially. So this is the neighborhood. So that means the pink color, this is the neighborhood of the domain side of the point A, and if f maps, it should be inside this green one. So that's the kind of geometrical way you can interpret the continuity of f at some point. Okay. Epsilon delta, the whatever epsilon delta I said, exactly this is a geometrical or pictorial way you can say. So that's something I have written. So for any given epsilon neighborhood u of f a, okay. So I want to talk about the continuity of f at a. So that means for any epsilon neighborhood u of f a, there exists a delta neighborhood v of a such that f maps v inside to the set A. F maps v inside the set U. That means f of v fully contained in U. So that's exactly pictorially I have written. So that means for any epsilon neighborhood u of f a, so this is my epsilon neighborhood u of f a, okay, this is my u, green one. So given that neighborhood, there should exist a delta neighborhood v. So look, this is the pink one, delta neighborhood of v, such that f maps the whole set v into that set fv, and fv should fully contain u, and that exactly pictorially I have drawn here. Okay, so now let's see the notions of continuous functions from several variable functions. So what I am doing here, okay, I am considering a functions f from some set D subset of Rn to Rm, let f be a functions, and as I already told you that to talk about the continuity of f at some point, I need the value of f at that point. So therefore I have to start with a point which is inside the domain of the function f. We say that f is a continuous function at the point x naught. What is the definition? Given any epsilon, there should exist a positive number delta which may depend on the point and epsilon, such that whenever x belongs to D and the norm of x minus x naught is less than delta, this should implies that norm of f of x minus f of x naught should be less than epsilon. Now, if you remember, actually I am just copying the definitions of continuity of functions from the real line to the several variable case just by replacing modulus by norm. Everything is same. So what I am doing, I am considering a point x naught inside the domain. I want to talk about the continuity of capital F at the point x naught. So what I am saying is that given epsilon, there should exist a delta, that delta should depend on the point x naught and also epsilon, such that whenever x, if I take x from the ball of center x naught and radius delta, so you can write in that case like ball of center x naught radius delta, whenever x belongs to that ball, the image, that means image of f of x, that means f of x, image of f at the point x, f of x should belongs to ball of centered f of x naught and radius epsilon. That exactly going on. Okay. So whenever the distance between x and x naught is less than delta, that means if norm of x minus x naught is less than delta, that should implies that norm of f of x minus f of x naught should be less than epsilon. If these things happen, then I can say that my function's capital F is continuous at the point x naught. Okay. So I have written, and if f is continuous at each point of D in the domain, then I will say that f is continuous in the set D. Therefore, we have seen that whatever the definition of continuity for real valued functions of real variable, similar sort of definitions also I can bring it in the context of several variable functions just by replacing modulus by norm, because norm is the corresponding distance we have introduced at the beginning of my lecture. Okay. So, some example let us see. So, let's start with the functions from Rn to Rn. So, f of x is equal to x, this is the identity function, this is always a constant, this is continuous function, this is easy to check, you can use that epsilon delta, then I think if I start with epsilon, take delta is equal to epsilon itself and it will work. Take another function g, say it is R2 valued, but domain is 4-dimensional Euclidean space. If I define g of x1, x2, x3, x4 by x2 comma x3, this is also a continuous function. Again you can use the definitions, like use the properties of the norm in R2 and R4, then you will be able to conclude that this is very nice function and this is a continuous function. In fact, later on already I talked about that given a functions in several variable, I will have the corresponding component functions, and in the case of limit, we already kind of familiar with that existence of limit of the original functions if and only if existence of the limit of the component functions. So similar kind of thing can I say in the context of continuity. That means if I have a functions capital F from Rn to Rm, and if I have say m components f1, f2, fm, now if I want to talk about the continuity of capital F at the point, is it equivalent by saying that my component function f1, f2, fm also continuous at that point? Answer is yes. That we will see in later slides. Okay. So, before that let me see few more examples. Okay. So, examine the continuity of the following functions. So, this is, you can take it as an exercise and you can easily prove that these are the functions, these are actually continuous functions. For example, this function f, which is a functions from R2 to R. This is also a nice function, you can easily check this is a continuous function. For example, if I talk about the continuity at 0, then you can easily check. So, that means what you have to do. So, first of all, it is a continuous function. Okay. So, how do I prove it the continuity of f at the point 0, 0? So, that means given epsilon, I have to find a delta neighborhood around the point 0, 0, and so that whenever I am taking the point from that delta neighborhood of 0, 0, the value of f at that point should also belongs to the epsilon neighborhood of f 0, 0. If this is the case, then I will talk about the continuity. So, for that you have to somehow estimate f of xy minus f of 0, 0. Okay. And what is this? By definition of the function, this is nothing but x plus y divided by 1 plus x square plus y square, because f of 0, 0 is 0. And if you remember some kind of similar sort of calculations I have done in my last slides, one slides before. So, this is certainly dominated by mod x plus mod y, because 1 plus, so denominator is 1 plus x square plus y square, which is always greater than 1. So, therefore, 1 by 1 plus x square plus y square, which is lesser equal to 1, and then by modulus of x plus y, which is lesser equal to mod x plus mod y, and also this is lesser equal to 2 times square root of x square plus y square. Okay. So, once this is done, then rest of the part is okay, because what you do, so given epsilon positive, choose delta is equal to epsilon by 2. So, I can make this is less than epsilon whenever x square plus y square, which is nothing but norm of x comma y minus 0, 0 in 2-dimensional, this is less than delta, and that will implies the continuity of f at the point 0, 0, and at the non-zero point you can do the similar sort of trick, you will be able to prove that this is a continuous function. Similarly, this function, so this is, so pi is a map from where to where? Pi is a map from Rn to R. So, this kind of function is called the projection functions. Okay. So, that means you see it is projecting the x1, x2 component to the ith component xi. So, one can also use the epsilon delta definition to prove that this is also a continuous functions. Okay. What about the next one? Next one is that, okay, so this says that start with a m cross n real matrix, define a linear map capital F by f of x is equal to ax, where x are coming from Rn. So, if I have these functions, then it is also a continuous functions, one can prove. In fact, if I have just Rn to Rm, the calculations will be little complicated. So, I want to just show you the continuity of f on Rn, but not on arbitrary n and m. However, I will just consider m is equal to n is equal to 2. That means, I have a functions capital F from R2 to R2, and then I will show that you see this is a linear functions, and that functions actually is a continuous functions. But proof I will do for m is equal to n is equal to 2, but the fact is true for any Rn and any Rm. So, that means take an m cross n real matrix, define a functions f from Rn to Rm by f of x is equal to a acting on x, this map is a continuous function. Okay. So, there it is the proof. So, I am starting with capital A from R2 to R2, which is a linear functions. So, I think you might have familiar with that the linear operator from Rn to Rn and matrix, these are equivalent. That means, if I have a linear transformation from Rn to Rm, then I can have a matrix which corresponding to that linear transformation, and if I have a linear transformation, then I can interpret that linear transformation as a linear transformation from Rn to Rm. So, this kind of equivalence you know. So, therefore, I am starting with a matrix A from Rn to Rn cross a matrix, then it will be I can interpret or corresponding to that there is a linear functions from Rn to Rm, and that exactly I am doing. So, start with a matrix. So, I have written a matrix M cross N, there it will induce or it will give a linear operator or linear functions from Rn to Rm. How? So, you just take the F acting on X is nothing but the matrix acting on the point X. So, that is what it is. Okay. So, now A is a 2 cross 2 matrix. So, I am writing this is A, B, C, D, these are the coefficients of the matrix, and action is what? F of F at the point X is nothing but the matrix acting on the vector X, which is nothing but x1 comma x2. And what is the simple matrix multiplications? So, first thing you should observe that if I calculate the norm of Fx, which is nothing but norm of Ax, which is dominated by some constant, some fixed constant k times norm of x, and this should true for all x in R2. That is very important. You have to observe this. Sometimes this is called actually boundedness. Anyhow, you forget about that term boundedness, because in functional analysis that kind of term is there, but since I am doing real analysis for the time being, you leave it. So, you just think that I need this kind of estimate to talk about the continuity of capital F at any point in R2. So, I need this kind of estimate first. Okay. So, that means this should be true where k is given by square root of a square plus b square plus c square plus d square. So, how the proof goes? So, what I will do reverse way. So, that means suppose this is true, then I will just do the reverse calculations. Once I am done that, okay, this is perfectly all right, then I will go back. Okay. So, suppose this is the true case, norm of Ax is less or equal to k times norm x, then of course, norm of Ax square is less or equal to k square norm x square. Then what will you do? You just compute the norm, because you know the matrix A, you know the vector capital X. So, you by matrix multiplication you know what is the vector Ax, and in the right hand side also you know the kind of vector x. So, you just do the norm calculation. So, if I have Ax, so Ax is a vector. If I know the Ax, it is the vector nothing but first row is that Ax1 plus Bx2, and the second one is the Cx1 plus Dx2. So, norm square is nothing but Ax1 plus Bx2 whole square plus Cx1 plus Dx2 whole square. So, what will be k square? Okay, already is there. If I take k is like that, so put k square, which is nothing but a square plus b square plus c square plus d square, and I have x1 square plus x2 square. Okay, then you do some algebra, then some square term get cancelled. So, in the left hand side you will have 2ab x1 x2 plus 2cd x1 x2. So, this is less or equal to this object a square x2 square. So, that means what? You have 4 times 8 terms will be there. So, 4 term will get cancelled. So, therefore, you will have a square x2 square plus b square x1 square plus c square x2 square plus d square x1 square. You take everything in the right hand side, then what will happen? This is plus this is positive, and which is exactly equal to this square. Okay. So, now you go back. So, that means this is true. So, that means sum of two positive square is always positive. So, that I know. So, therefore, now you go back. So, that means start with this factor. Okay, a, b, c, d is given, x1, x2 is given. So, therefore, you take the square of this and this square, it is positive, which implies this, which implies this, which implies this, which implies that, where k is nothing but this object, and hence this is equal to true where k is this one. Okay. So, first I assume that it is true, then I am doing reverse calculations and somehow justifies that yes, whatever the conclusion I am done, this is the correct and it is universally true. That means sum of the square is positive. Then you go back and you show that yes, if I start with this object, I will end up with this inequality, and where k is this. So, therefore, if I have a map, or if I start with a 2 cross 2 matrix, if I define a map from R2 to R2 where action of f at the point x is nothing but Ax, then first observation is that norm of Fx, which is dominated by k times norm x, where k is a fixed constant, which is nothing but the sum of the squares of the elements of the matrix A. Once I have this estimate, then using the linearity of the map capital F, I can conclude that capital F is a continuous function. Okay. look, so what I said, so f is a map from R2 to R2, it's a linear function defined by this, where A is a matrix, I just said. Now, if k is equal to 0, then go back, if k is equal to 0, then right hand side is 0, so therefore left hand side norm of fx is 0, and which implies f of x is 0. That means if k is 0, then f is only a 0 map, and which is a continuous function. There is nothing to prove. So, I assume that k is strictly positive. Now, we show below that. So, below this is the justification, I want to show that capital F is a continuous function. Okay. So, let take any point x naught, any arbitrary point in R2, I want to show that a capital F is continuous at the point x naught. So, I will use just epsilon delta definitions. So, what I am doing, so start with any epsilon positive given. So, choose delta, which is nothing but epsilon by k. Here given epsilon, I am giving explicitly what is your delta will be. So, delta is epsilon by k, such that whenever the distance between x and x naught, which is less than delta, which is exactly equal to epsilon by k, then you just do the estimate. So, what estimate I will do? I will do the estimate norm of fx, norm of capital F acting on x minus capital F acting on x naught, and what is that? So, this norm, which is same as, since f is linear, which is what? F of x, or okay, keep it like that, f of x minus f of x naught, to write. So, f of x I know this is ax, that is why I have written ax, and f of x naught, this is ax naught. Now, A is a matrix. So, that means it's linear, or f is linear, whatever it is. So, therefore, I can take a common, which is nothing but x minus x naught. Now, in my last slide, I proved that norm of ax, which is dominated by k times norm of x. So, therefore, this is k, and what is my x? Norm of x minus x. Okay, this is a typo, this should be norm. One more, norm. Okay. But I am taking x minus, I am starting with x as that norm of x minus x naught, which is less than epsilon by k. So, therefore, if I, so that means this should be less than k times delta, and what is delta? Delta is epsilon by k. This is the identification kind of adjustment, and which is nothing but epsilon. So, that means what I have done is that, so I am starting with epsilon, I am saying take delta is equal to epsilon by k, then I am saying that if norm of x minus x naught is less than that delta, then the corresponding distance between capital Fx minus capital Fx naught is less than epsilon, and that is nothing but the definition of continuity, and therefore, capital F is continuous at x naught, capital X naught, and capital X naught is an arbitrary point in R2. So, therefore, capital F is continuous everywhere. So, this is kind of proof from R2 to R2. However, you can also prove in similar way with little bit kind of difficulties will be there, at least in the calculation process, but you can prove that capital F is also a continuous function from Rn to Rn if I start with a n cross m matrix. Okay. So, now there is something, so two things. So, what is that? So, now I am considering a functions from R2 to R. Okay. So, now I am starting with the functions f from R2 to R. Okay. So, this is, that means real valued functions from two dimensional Euclidean space. What I am doing, first I am considering a point, fixed point, y naught is fixed. Now, once I fix my point y naught, then I am defining a functions g from R to R, which is nothing but g of t, which is f of t comma y naught. So, whenever I am fixing the point y naught, now I am having a functions from R to R. So, that means what is my function g? G is a map from R to R, and how g is defined? G of t, which is nothing but f of t comma y naught. So, therefore, given a functions f from R2 to R, fixing a point y naught, define a function g from R to R, real valued functions with real variable, like g of t is nothing but f of t comma that y naught. Similarly, this is in the second component I am fixing y naught. Now, if I fix the point x naught in the first component, again also I am defining, introduce a function h, which is nothing but h of t is equal to f of x naught comma t. Here x naught is fixed. Then also I can define a functions from R to R, where h of t, which is nothing but f of x naught comma t. So, that means given a functions f from R2 to R, I have two real valued functions of real variable. First, keeping the variable y naught fixed, I am having a functions say g from R2 to R, defining g of t is equal to f of t comma y naught, and then keeping x naught is fixed, I am having a function h from R to R, h of t is equal to f of x naught comma t. Now, the natural question is there any relations between the continuity of f and the continuity of g and h, these component functions, in that way? Component mean in that way. I am keeping one variable fixed, thinking about is a function of real value functions of real variable. So, now the question I am asking is that, is there any relations between the continuity of f and continuity of g and h? That means, is there any relation whether continuity of f implies the continuity of g and h, or continuity of g and h implies the continuity of f? Let us see. Okay. So now start with the functions f from R2 to R, this kind of function I am taking. What? So it is if xy is non-zero, this is xy by x square plus y square, 0 if xy is equal to 0, 0. So now if I fix a point y naught, okay, define I have defined a function g from R to R, gt is equal to f of t comma y naught. Now if y naught is non-zero, then what will happen? Just put the value of y naught in the definition of f. So what is your g of t is nothing but t times y naught divided by t square plus y naught square. So this is the functions from R to R. Okay. Very nice. If y naught is equal to 0, your g function is 0 because of the numerator you have x times y naught is 0 means these are 0 functions. Now if I fix x naught, what sort of function I will get? H. So h again is f of x naught comma t. You know the value of f at xy. So if I put x is equal to x naught, so I will have this kind of functions, and if x naught is equal to 0, I have h2 is equal to 0. But what can I say from that? So from that I can say that this function, if of course if y naught is 0, x naught is 0, I have g function is 0, h function is 0, and 0 function is a continuous function, perfectly alright. Even if y naught is 0 and x naught is 0, I have this kind of functions, but this is also a continuous function because this is a quotient of two continuous functions. So denominator is just function t times some fixed constant, so that means it's a constant functions. Numerator is t times y naught, denominator is t square plus y naught. This is also polynomial function, continuous function. So that means numerator is a polynomial of degree 1, denominator is a polynomial of degree 2, and polynomial function are constant functions. So therefore the quotients of two polynomial is a continuous function. Therefore g is a continuous function. Similarly h is also a continuous function. However, let's see the continuity of small f at the point 0, 0. And by looking at the functions, I can easily say that these functions is not continuous at the point 0, 0. Why? Because I already discussed in my last slides that the limit of this function at xy approaches to 0, 0 will not exist, does not exist. That I already proved. Why? This is very simple. You just take y is equal to mx, this path. So that means you have 0, 0, you have 0, 0. I am just approaching 0, 0, y is equal to mx path. Then what will be the value? So you just replace y is equal to mx. So what will be the value? The value will be, I think, m divided by 1 plus m square. So that means if I approaches to the origin from the line y is equal to mx, the value of the functions along this line will give you the value m by 1 plus m square, and if m varies, it will give you different values. So that means if I coming from y is equal to x, it will give you 1 by 1 plus 1 square, that means it is give you half value, and if I come through y is equal to 2x, so it will give you 2 by 5 value. So that means I am approaching to the origin from two different lines, but the corresponding value of the function approaches to different points. So that means limit does not exist. Since limit does not exist, so therefore function is not continuous. So therefore this is the example says that even if my functions small f is continuous from R2 to R, but the functions I have introduced g and h, they okay. If I have a function f from R2 to R, it is not a continuous function at the point 0. However, the functions I have introduced g and h, they are continuous functions. Okay, so that's what I have written. So in the previous slide, for each fixed y naught, the function g is continuous. For each fixed x naught, h is a continuous function. However, the function f is not continuous. So therefore, what is the conclusion? Conclusion is that continuity of g and h do not guarantee the continuity of f. That's the conclusion I can make. Let's see whether converse kind of things, whether can I have some kind of argument. So let's see. Yes. So this is another example. So I have a function f from R2 to R, which is defined like that. I think this kind of functions you might have seen in my earlier slides. Okay, how I define? If xy is non-zero, this is x sin 1 by y, and then y sin 1 by x, 0 if xy is 0. Okay. So now let's see how the function small g and small h looks like from R to R. So therefore, if I fix a point y naught is equal to R, gt is equal to f of t comma y naught. Now if y naught is non-zero, so gt is a function which is t sine of 1 by y naught plus y naught times sine of 1 by t if t belongs to R, and if y naught is 0, then you see, say y naught is 0, then gt is 0, because yes, y naught is 0, that means what? If y naught is 0, that means xy is 0, that means this is 0, so not an issue, so therefore this is 0. So gt is 0. Similarly, if I have a fixed x naught, then I have a function h, which is the definition h t is equal to f of x naught comma t. Okay. If x naught is non-zero, this is x naught sine 1 by t plus t times sine 1 by x naught, and if x naught is equal to 0, that means I am in this case, so therefore this is equal to 0. Now let's see about the continuity of f, continuity of g, and continuity of h. So now by looking at the functions, if y naught is equal to 0 and x naught is equal to 0, then both the function g and h are continuous because they are 0 functions. Let us see if y naught is non-zero or x naught is non-zero, then what is the function g and h are continuous. Okay, look, if y naught is non-zero, by looking at this function I can immediately say that this is not a continuous function. Why? Because the function g involved the term like sin 1 by t. And the functions I know, if f of x is equal to sin 1 by x, I already discussed similar sort of argument in my last slides, that this kind of functions, if it have sin of 1 by x term there, only sin of 1 by x term, this is not a continuous function. You can have the sequential criteria and show that this is a discontinuous function. So therefore, since sin 1 by x involves in the function g, it is not a continuous function. And similarly, you will sin 1 by x involved in h, so then sin 1 by t involved in h of t, so this is not a continuous function. However, the function I started with f, I can prove that this f, in fact, I have shown the existence of limit of this kind of function is as xy approaches to 0, 0, right. So what will happen? So this function f actually is a continuous function at the point 0, 0, but the function g and h, they are not a continuous functions. So let me see what sort of things I have written. Okay. So in my previous slides, so I have a function f which is continuous function on R2, but if y naught is non-zero, it involves sin 1 by t, so therefore it is not a continuous function at 0. If x naught is non-zero, it involves again sin 1 by t, so therefore h is not continuous at 0, 0. However, the function f is continuous in R2. So look at the function same. So of course, so if xy is non-zero, this is a nice function, it's a continuous function. So only you have to check at 0, 0 what sort of problem is going on. Again, you can easily estimate it. So like this kind of estimate I already done in my last class, like for f of x y minus, in fact this lecture as well. So what is this? This is same as x sin 1 by y plus y sin 1 by x, because f of 0, 0 is 0 value, and this is dominated by what? Mod x plus mod y, because mod sin 1 by y and mod sin 1 by x is dominated by 1, and this is less or equal to 2 times square root of x square plus y square. Now you just play the epsilon delta argument. So given epsilon, choose delta is equal to epsilon by 2, such that whenever norm of xy minus 0, 0, which is less than delta, this is less than epsilon, and therefore my function is continuous at 0, 0. And rest of the part you also prove that this is a function, is continuous functions in R2. So what is the moral? So moral is that, so continuity of f from R2 to R at 0, 0. Okay, I am just proved the continuity of f at 0, 0 does not guarantee the continuity of g at 0 and continuity of h at 0. That is very important for each xy. So that means I have two set of examples. One, I have examples of f which is not continuous at 0, 0. However, the function g, h are continuous. Here is some kind of different. That means I have the continuity of f at 0, 0, but I do not have the continuity of function g and h at 0. Okay. So that means what I am trying to say is that continuity of f from R2 to R will not guarantee the continuity of g and h, and continuity of g and h will not guarantee the continuity of f. So there is no such kind of vice versa relations between the continuity of f and continuity of g and continuity of h. This is just one simple slides. It is the algebra of continuous functions. So that means if I have a functions from Rn to Rm, and if I have function g from Rn to Rm, and if I take the point x naught is in D, then if f and g are continuous at x naught, then the following functions are also continuous at x naught. That means sum of two continuous function is also continuous. If I multiply by scalar, that is also a continuous functions. Inner product between two functions f and g, that means it's, if I take the inner product, it becomes a scalar value. Also, it is also a continuous functions. So, okay, in fact, inner product is a continuous function. In that way, you can prove norm of f. If I take this function, that means x goes to norm of fx. This is also a continuous functions. There are various ways you can prove, like capital F is a continuous function, norm is a continuous function, then x goes to norm of fx, it is also a continuous functions. Quotient is also a continuous function, provided quotient makes sense, that means m is equal to 1 and g of x naught is 0. That means sum of two continuous functions, scalar multiple of a continuous functions, norm of continuous functions, inner product between two continuous functions, and the quotients, these are the kind of algebra of continuous functions. Like similar sort of things I have seen in the case of limit as well. Okay, so I think I should stop right here. So in my next class, I will talk about little more about the continuity of f, and as I already said that if given f, if I have a component functions, then is there any relations between the continuity of the original functions and continuity of the component function. I think I should stop here. I think next lecture I will talk about that. Thank you.